Coming up on Dr. Kiki's Science Hour, we're talking about the science of catastrophes with Dr. Donald Prothero of Occidental College. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with Dr. Kiki, episode number 91, recorded on Thursday, April 14th, 2011. It's a catastrophe. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies streamed to your PC, Mac, or TV instantly. Plus, get DVDs by mail in about one business day. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to Dr. Kiki's Science Hour. I'm Dr. Kiki, and I'm back from maternity leave. I've been gone for a bit over a month now, probably about a month and a half that I haven't been doing the show. Thanks everyone for continuing to watch and for supporting the efforts of the guest hosts that took over while I was away. We had some wonderful guest hosts, some great interviews while I was gone, and I just want to say thank you to Jerry Ellsworth, to David Harris, to Phil Plate, to Brian Mallow, to all of you for hosting the show while I was away and just making it awesome, fighting the good fight, carrying the torch of the Science Hour for the last month. But now it's on to the present. We keep going at marching ever forward, and I hope to continue to do this show for a long, long time, as long as I have a babysitter. That's the new key. Anyway, this is Dr. Kiki's Science Hour, episode number 92, and we have a catastrophic show for you today. I might put it that way. We're joined today by Dr. Donald Prothero. He is a professor of geology at Occidental College, and he is a lecturer in geobiology at the California Institute of Technology in Pasadena. He earned a master's degree, an MPhil, and a PhD degree from Columbia University, and a BA in Geology and Biology from the University of California at Riverside. He's the author, co-author, editor, or co-editor of over 25 books and over 200 scientific papers, including 5 leading geology textbooks and 3 trade books. He's on the editorial board of Skeptic Magazine, and has served as an associate or technical editor for Geology, Paleobiology, and Journal of Paleontology. He's a fellow of the Geological Society of America, the Paleontological Society, and the Linnaean Society of London. He is the vice president of the Pacific section of the Society of Sedimentary Geology. And in 1991, he received the Schuchert Award of Paleontological Society for the outstanding paleontologist under the age of 40. He's also been featured on television and in lots of documentaries on channels ranging from the BBC to the History Channel, National Geographic, and others. We're here to talk today about his book that's just out, Catastrophes. Catastrophes, earthquakes, tsunamis, tornadoes, and other earth-shattering disasters. So there's a science behind all this, huh? Welcome to the show. Thanks for joining us, Don.
Thank you very much, Kiki. I'm really pleased to be here.
I'm glad to have you on. It's great. I'm excited to talk about catastrophes in the sense that so often, as happened recently with the Japanese earthquake and tsunami, we experience something that is catastrophic, and we experience it in a very human way, which is to experience it as its own event in space and time, and we end up only looking at it as this huge disaster, and then it kind of goes away. And then the next one comes and it's its own big disaster. And we really, as humans, don't I guess, don't look at things in a very disasters or catastrophes in a very scientific manner. Do you have any ideas about why that might be?
Yeah, that is a big problem. Most people think in very short terms. They don't remember stuff past a decade or two in most cases. But we as geologists have very, very long time perspectives. We think about millions of billions of years as if they're nothing. And so over long time perspectives, you can see, patterns of earthquakes over decades or centuries, or patterns of other events. And then you start to understand them in a bigger picture. And they don't appear to be just individual events anymore. They're usually part of a bigger picture.
In terms of trying to change that and being able to give us that bigger picture. I mean, in the book you've written about lots of individual events. How have you tied them together to kind of give that bigger picture?
Well, most of these events are actually part of a geologic pattern where you can see they have common threads, or there's common mechanisms that explain most of them. And the bigger issue is that as geologists, we try to not only see them as events in a sequence, but we try to understand what causes each one, or if they have a similarity or difference in the geologic forces that cause them, and that helps us better understand when they're likely to occur in the future. For example, earthquakes. Earthquakes have a lot of things in common, no matter what kind of earthquake they are. But there are earthquakes that, for example, like the recent earthquake and tsunami in Sendai, Japan, are formed by subduction zones where one plate pushes beneath the other, and that meets a tremendous amount of stress. Those have always been the biggest earthquakes in recorded history. Very different from the type of earthquakes we experience here in Central and Southern California, where we are talking about two plates that are sliding past one another. And in that case, they generate different kinds of emotions. They also generate different degrees of energy. They're destructive, but in a different way.
Can you talk a little bit about the different types of destruction?
Well, the thing you see with these big earthquakes that are generated by subduction is that they have tremendous energy in them, because you have a whole plate, one sliding beneath another. And in that process, you do a tremendous amount of energy released when that plate slides really quickly. It makes a slip. And that generates this big energy. And in the case of the Japanese earthquake, if it's offshore, that energy also goes through the seawater and manifests itself as a big wave, a tsunami, which then, as we saw if you watch the video footage from Japan, was actually in most ways far more destructive than the earthquake itself. By contrast, here in California, virtually all of our fault line that we're worried about is inland by quite a bit from the ocean. There's only a couple of places where the San Andreas goes out to sea and then comes back again. And all recent earthquakes the last century or so that we've had in the San Andreas and on the related faults are inland, so they don't generate a tsunami. Or very little of a tsunami. And what they do instead is they propagate in different ways, in different directions, and it all depends on where the fault moves compared to where the population and the structures are. Depends, it will give you more or less damage. So in some cases, they may be far enough from structures that they don't cause as much damage as they did in Japan, where just about any earthquake in Japan is close to a populated center. It's a very heavily populated area.
Right, and I think that's one of the big points to make about any kind of catastrophe, earthquake, tsunami, volcanic eruption, anything. The amount of destruction that is pertinent or salient to the human experience has to do with how close that event is to a population center. Right.
For example, the biggest earthquakes in U.S. history, we're pretty sure the biggest one ever happening in American history was in 1811, 1812, in a place called New Madrid, Missouri, which is underneath the Mississippi River now, close to Memphis and St. Louis. And but in 1811, almost no, at least non-Native American populations lived in that area. There was just a few thousand people living in cities like early Memphis and early St. Louis, and a few more in New Orleans, but not a large population, and certainly not a large number of structures in 1811. And so even though that earthquake was so powerful it toppled steeples in Boston, and this is all the way from Missouri, it didn't make nearly as much an impression on us as it could have, just simply because there were not a lot of people, not a lot of structures in the way. And so that has a big effect. You know, historically, the quake was not as damaging as it would have been a century or two later. Likewise, here in Southern California, the biggest earthquake in recent recorded history would be the 1857 Port Tejon earthquake, which broke the San Andreas just north of where I am right now, in the stretch from Palmdale down to San Bernardino. But in 1857, this is 3 years before the Civil War started, there wasn't much population in Los Angeles. There were not very many large buildings. What few buildings were fairly large, like the old missions, fell over. But most of them were simple structures that didn't get much damage. And, of course, not that many people to feel it in the first place, and not hardly anybody living up close to the epicenter. So, again, 1857 was just too early for people to get the sense how big these earthquakes are. But that's the kind of earthquake we're expecting now. It's the one that's considered overdue in our region. The one we talk about is the big one. And when that happens, of course, it'll have a much bigger effect now, whenever it does happen, than it did when it was first last observed in 1857.
What are what you mentioned earlier about looking at the geologic record of events like these to be able to maybe predict when events might happen again? What kind of accuracy or what kind of predictability can we get from looking at the past at events like this?
Well, in the case of earthquakes, there's two kinds of prediction. Most seismologists and people who work on this do what we call long-range prediction, talking about things in a framework of months to years, and say this stretch of fault is what we call a seismic gap. It's been quiet for too long, and yet it has a history of big earthquakes, so we are predicting that it's due to break, and that when it breaks, it'll be big because it's not releasing its stress very slowly like other stretches of a fault might. And so, for example, just before the 1989 Loma Prieta quake that stopped the World Series in the Bay Area, there was already predictions with a year ahead of it from the U.S. Geological Survey saying this is one of the most dangerous stretches of the fault now. We're predicting this quake to occur, but they cannot be more specific than that. And that's basically all the geologists still can do after 50 years of trying to get earthquake prediction right. What you'll hear a lot of people try to find out or try to ask for is short-term prediction, warnings of a few hours to a few days in advance, and there is no, at this moment, magic bullet for that. There have been a few successful short-term predictions, and then they turn out to be flukes, that there's just as many false alarms as there are good predictions. And I spent a lot of time, by the way, in blogs over the last couple of weeks talking about some of these false prophets who go out there and make these predictions, and nobody realizes that they're all charlatans. They have no scientific credentials, and there's no basis for what they're predicting at all. People would love to have warnings of a few seconds to a few hours before a quake, but there is no physical way that can happen yet. And the primary reason that we think this is the case is that back when I was a graduate student at Columbia in the 70s, they were all excited about this new theory called dilatancy theory that would predict the various events occurring just before an earthquake. When the ground was strained, you'd see change in electrical conductivity and ground pressure and micro earthquakes and all the rest. And so they were all excited this would be the great technique that would tell us when earthquakes are going to happen on short notice. And it did predict one earthquake in Haicheng in 1975. And so they successfully did that, thought they had the problem solved. And 17 months later, a huge earthquake happened in Tongcheng in China, killed 750,000 people, and there were no precursors. And that has sort of been the sobering sort of a lesson we've learned from this, that all earthquakes are very different, no two are alike, and the method that might work for one earthquake may not work for the next one. Therefore, at the moment, we don't have any reliable way of predicting earthquakes in general.
Yeah, from what I've read, it seems as though the predictability is basically there's a lot of pressure, a lot of stress on this particular fault, say the Hayward fault, but they can only say, give it maybe a 60% likelihood of having an earthquake within the next 30 years, or but the actual minute to minute predictability is still very difficult to pinpoint.
That's right. In other words, they've looked at this fault, they've looked at its history, they have a pretty good sense of how often it breaks. So if they see that it's way overdue compared to the data they have in front of them, they'll give you a window of probability or predictability in terms of statistics. But people like simple answers. They don't want something that's a statistical probability or within 95% within the next 30 years doesn't help most people making decisions. So therefore, people either don't understand it or they misunderstand it. And then they go and turn to quacks who want to tell them what they want to hear, have some sort of weird way of predicting an earthquake. And so we end up with problems like that. And there's a good reason seismologists are fairly leery about making very specific predictions, the ones who are actually competent seismologists, and that is we live in a very litigious society. And if you think about that, if you make a prediction and it doesn't come true, you're sued. Or if it does
Right.
come true and they somehow decide you didn't do enough job to predict what they thought was the seriousness of the earthquake, they could also sue you. Either way, you lose. And this just happened last year in Italy. They had that big quake in Italy a year ago, and people were suing the seismologists in Italy. In fact, nobody in the seismology community would ever say that it's reasonable to predict earthquakes, yet people wanted to sue the messenger, even though they were smart and did not predict the earthquake. There wasn't any way they could do that. So
just find somebody to sue and sue them. That is just insane. From the standpoint of I guess being a seismologist, somebody maybe working for the USGS or other, I guess the best advice you can give anybody at this point in time is have an earthquake preparation kit.
Right. I mean, the problem is that we are pretty confident within, of course, statistical limits about certain stretches of the certain faults being very much overdue within a window of a certain number of years. And beyond that, you cannot at this moment say anything with more confidence. And no reasonable seismologist who knows what they're doing will say that. And so, therefore, I tell people, act as if it will happen tomorrow. Because you cannot predict it. You just have to go ahead and prepare, because it will happen. It may not happen while you're still there, but you've got to pretend it will. And so, for example, our family has an earthquake kit all ready to go when this happens, because down here in Los Angeles, we have very significant problems if the major stretches of any of these faults thought to be overdue, like the San Andreas to the north of us, or the Newport Inglewood, which is right underneath all the coastal communities. All those earthquakes have happened in the last century. And in the current situation, when Los Angeles experiences that next big quake, whichever fault goes, we can expect it'll be much worse than Northridge 94. The freeway system will be completely shut down because of so many fallen overpasses and broken, road stretches. You won't be able to go anywhere because of the broken roads, especially because we're locked in by mountain passes to the north of us, which will almost certainly be closed. And we will have all of our water shut off, because all our water comes here from aqueducts from other places, including Northern California, from your part of the world. And we will also probably not have electrical power for a while or anything else. And cell phones will be down. And so I always tell my students, not just an earthquake kit, you better have a system where you can get a landline hooked up in your house if you have a chance to do that, and also an out-of-state contact, because all the calls within a affected area will be jammed. The only place you might have a chance of reaching someone to let them know you're okay or how things are working is to call out to someone who's not in the zone. But the basic idea is that you just have to have that attitude that you don't know when it's going to happen, therefore you prepare as if it's going to happen tomorrow. And of course, when you get an earthquake kit, you don't just leave it in the garage for a decade. You should go and check it each year. And the food tends to spoil, the water tends to leak. So you go and replace it, use up what's still edible, and put more stuff in, so that when the thing happens, you're prepared. The biggest issue here in Southern California will be water. If you're sort of stuck at home and can't go anywhere, and there is no water coming through the pipes, and especially if it's a summer here, you're going to be thirsty really fast. And there's a simple way to deal with that, and that's the reason, for example, why all water heaters in houses in this part of the world are always strapped to a firm, post or whatever, because even if your water heater is broken loose, if it's still standing upright, it's got a huge amount of water in it. It's fresh water that you can use for several days before things get back to normal. So
something good for people to think about. Yeah.
And it applies to the Bay Area too, and even inland of the Bay Area. I mean, Davis is not that far from. In fact, nobody in coastal California can really be comfortable, because there are faults virtually anywhere you look in California, even in the Central Valley and up the coast. And so just certain areas are more risky than others. But the Northridge 94 quake happened on a fault we did not know exist until it moved, and then we found out about it. And that's something that makes you sober when you think, okay, they mapped the faults, there's none close to me. Well, there's lots of faults we don't know about yet.
How do they go about finding a fault? I mean, until it moves, is there any way that you can have any inclination?
For faults that are active and ones that we fear, there's always small amounts of motion on them. They have little earthquakes in the 2 or 3 range almost all the time. And so, they're not hiding from us. We can usually see them. And the other way you find faults, and these generally are faults that are no longer active, is by geologic mapping, by walking miles and miles across the terrain and recording what rock units you see on a map, And when you see big places where there's two units that don't match and they're abruptly once against another, even if you can't actually see the fault on the ground, you can be inferred there's got to be a fault between them. But most of those cases where there's no activity now, you can presume that fault is probably extinct and no longer active, although we don't know that in every case. Some of them do reactivate after time.
What about faults that are beneath the ocean? So similar to what happened with Japan's earthquake and the earthquake that caused the tsunami in Indonesia a couple of years ago. How do you find those faults? Are we using satellites to track movements, vibration of the surface of the planet, or?
Well, yeah, that is used, but for the faults you're describing, the big plates that are plunging beneath one another, like in Japan, like in Indonesia, like in Alaska, between the Aleutians, these are actually well known. We know exactly where they are. They're giving us small earthquakes almost all the time. So we can see their position in 3 dimensions quite well. But what we cannot do is predict when they're going to release a lot of energy all at once, as they did in Japan last month. That part, Japan always, sits right on this time bomb. Its entire country is built right next to this huge subduction zone. The one plate plunges beneath the other. And they have no choice. That's where they live, and that's normal for their part of the world, as it is for the Philippines, as it is for Indonesia. And so they just simply, as we've heard widely in the media since the Sendai quake, they tend to be as well prepared as any nation is today. But even that is no good if you're too close to the earthquake. As you saw, Sendai, had no chance. It was so close to the earthquake that what wasn't destroyed by the shaking was, of course, wiped out by those monster walls of water that came in, and no building could stand up. They fell over like matchsticks if you watch the video footage.
Yeah, the video footage is quite something to see if you haven't seen it. Although I'm sure a lot of people have spent time on YouTube and other internet channels watching stuff occur around the globe. A lot of the damage that occurs, we have these earthquakes. So the 9.0, 9.1 Sendai quake, it caused its own damage, but the tsunami itself was so much more devastating to the coastal populations. Do these go hand in hand? We saw with some of these 7.0 aftershocks that there were not tsunamis, even though there was a tsunami warning. Is there any understanding of, you have this particular type of a particular type of interaction between the plates? Are they always interacting in a way that should be pushing water or falling, or are they just slipping in different ways around each other?
Well, in the case of the Japanese situation, the plate's always moving the same direction. It's the Pacific plate gradually being pushed underneath the Asian plate. And sometimes it slips very quickly and releases a lot of energy, which is the big quake we had a month ago. The aftershocks are 2 to 3 orders of magnitude weaker, right? Remember, the scale, the Richter and moment magnitude scales we use for these things, a jump from a 7 to an 8 is a jump of 10 times on the scale and about 31 times as much energy. So you drop from a 9 to a 7, and that's about 100 times less on the scale. It's a 2 orders of magnitude difference. And so people don't realize that it's not a tiny amount smaller, it's a lot smaller. And therefore, yes, you might have generated tsunamis, but they would never have been as big as something that was 9. And so the warnings come out, and maybe the waves are visible, but they're nothing like the walls of water that a 9 can generate. And it also could be that some of these aftershocks are in different parts of the fault that don't force the crustal rock up after the quake that much. The key to the tsunami is that you have to have a motion on the seafloor that pushes upward and forces essentially water to be pushed upward as well and propagate out in this big sort of giant ripples from a pond in all directions. That's what a tsunami is. It's a big wave that propagates from a point source of energy. And so, if it's just slightly different in terms of where it is in position at the coastline or how big the energy is, and again, 7 to 9 is 100 times different, then, you get either a much smaller tsunami or none at all.
One question that that's coming from the chat room, there's the question of whether or not we can mechanically stimulate earthquakes. And I think this is really interesting because a lot of people are talking these days about physically affecting our atmosphere because of climate change. So what can we do to increase rainfall, or what can we do to increase carbon sequestration? What can we do to decrease the amount of sunlight that gets to the surface of the planet? Can we physically do anything to the crust of the planet that would change the likelihood of an earthquake or a tsunami?
Yes, that has actually been known for quite some time. It was always discovered, like many things in science, by complete accident. As we've heard, most of the great discoveries in science happen when you're not looking for them. And it was actually at a military base outside Denver they first found this, and also in an area in Russia where they had a big reservoir. And that is, if you have fluid injected into the ground, it tends to lubricate a fault zone, and the fault zone will then start to slip, but it tends to slip in small earthquakes. And if you take the fluid out of the ground and pump it out or do whatever, or in the case of this Soviet reservoir, if the reservoir was in a drought period and there was not much fluid pressure down and below it, then the earthquake stopped happening because the ground tended to lock up when the fluid pressure was no longer separating the grains. So this has been long known. This is 30, 40 years now that people have known this and occasionally experiment with it. And there have been sort of mad scientist proposals out there of ways we might try to control earthquakes by releasing them slowly. You can imagine a scenario, for example, you have, say, a fault line running across an area, and you have wells drilled in a zigzag pattern across them. You could take a rig and pump all the water out of 2 wells to lock the 2 ends of a fault, and then force the water into a well between them, and try to lubricate just that straight into the fault that's between the 2 locked ends, and presumably release the energy from it. And then once that's done, then you would drain the water back out of it, lock it, and then pump water into the next one down the line, and then try to release that little stretch one by one. So you sort of unzip the fault with less and less, as you go down the set of wells, you would unzip it and release the energy in small pieces. And this has been talked about a lot, but there's 2 major hurdles. One, of course, is the cost, which is always an issue. But the bigger hurdle is the one I mentioned earlier, is this litigious society. You try to do something to mess with Mother Nature, and if anything goes wrong, guess who gets sued? And so people are very careful and usually really very cautious about trying to do something like that, because they rightly feel we don't really know that much about this situation. We're not confident that we can just unzip an earthquake if we try this scheme, and especially if it goes wrong and release it in a way we didn't intend. It would completely destroy the people who are involved. So, there's just, unfortunately, this makes for a society where we're not willing to take risks either, and often could be doing useful experiments that might solve this issue, but nobody's going to take that chance if they are going to be sued for millions.
Right. Maybe the only place that they would take that chance is someplace out in the steppes of Siberia where there aren't that many people, or in the Alaskan tundra.
Well, or in the People's Republic of China, where there is very little in the way of individual freedom to do that kind of thing. Nobody sues the government of China, that's for sure. And so they can tell people what to do. And of course, in many cases, like the controversial Three Gorges Dam and so on, they can basically drive whole populations out of their homeland just to flood the country for a reservoir. That's a kind of a different issue as to political issues of freedom and choice that people have in those countries. But the trade-off is that the Chinese can make decisions on a national level that we can never make. And whatever you think of their system of government, they right now, for example, in other areas are doing things that we can't ever get ourselves up to do, like investing heavily in modern technologies, especially low carbon energy technologies. They've jumped way ahead of us now, and that's because they can make a decision top down and go ahead and do that and put the force behind it in a way that we can't even get our Congress to agree that global warming is real, let alone the population.
Right. I'm going to take this opportunity very quickly to have a word from our sponsor. This episode of Dr. Kiki's Science Hour is brought to you by Netflix. Netflix delivers movies directly to your home, and that saves you time, money, and hassle, and gives you freedom of choice as well. You can instantly watch thousands of TV episodes and movies, or have them streamed directly to your PC or Mac, streamed directly to your TV via a Netflix-ready device, including the Xbox 360, PS3, or Nintendo Wii. You can also get DVDs by mail in about 1 business day if that's what you choose to do. Watch as many movies as you want, anytime you want. There are never any late fees and no due dates, which is really great because I actually have a bunch of DVDs that need to be mailed back. I've had them for about a month. Getting myself.
I can't imagine why you don't have them now.
I know. So we like to choose, give you a suggestion of movies or shows to choose from. My suggestion for the Netflix streaming pick of the week, this is what I'm watching this week, is Buffy the Vampire Slayer season 1. Season 1, if you want to talk about catastrophes aside from earthquakes, tsunamis, tornadoes, and other things, Buffy the Vampire Slayer, she's dealing with vampires and the Hellmouth and all that kind of stuff. And she's in high school. So anyway, I went back in time, taking a look at this old series that offered up a lot of enjoyment. Additionally, when I'm not watching Buffy the Vampire Slayer, so this is, I guess, choice number 2, Doctor Who, the BBC series. You can go back and watch that series as well. It's a great science fiction series where Rose and the Doctor travel through space and time, defeating all sorts of alien villains across the universe, even in parallel worlds. So there's not just catastrophes here on our planet. They're everywhere. And, you can enjoy a little bit by checking out the streaming options like Buffy the Vampire Slayer or Doctor Who, which are available through Netflix instant streaming. You can instantly watch these shows or choose from thousands of other TV episodes and movies when you register for a free trial membership. And to do that, you go to netflix.com/twit, TWIT. Be sure to sign up for your free trial at netflix.com/twit. And we thank Netflix for their support of This Week in Tech. Back to the show, back to the catastrophes. One thing that I wanted to ask was, before we went into the break, very briefly, you started talking about how China's government, being that it's not a democracy, they're able to have top-down control over what experiments that they do, what large public works projects they put into place. I'm really fascinated by the idea catastrophes as molding the future of humanity. And so throughout history, what kinds of catastrophes have you seen, have you researched, and maybe included in your book, that have really had an impact, a lasting impact in the path that humanity has taken?
Yeah, there are actually quite a few that are thought to be important. I mean, there's some where you can historically show that the course of civilization in some ways was changed by a big event. The very first event I mentioned in the book, of course, is the famous 1755 Lisbon earthquake, which was the biggest earthquake in recent European recorded history. And it hit at a time when Europe was still in the sort of a late medieval period and still very antiquated, especially in a country like Portugal, which was, medieval in lots of ways and pretty much in the power of the clergy. And also at a time when there was a sort of Leibnizian idea that this is the best of all possible worlds, is a very familiar phrase from that way of thinking. And they talk about that earthquake as changing European thought, because this is one of the most pious cities in Europe at the time, the most religious cities, and it was almost utterly destroyed by this huge quake. And it ended up changing everyone's idea about this optimistic philosophy of Leibniz and others at the time. The most famous work which emerged from that, of course, was Voltaire's Candide. And the satire that he does on this entire world viewpoint, where, as if you recall the novel, Candide experiences every possible calamity that can happen to a human being, including being in Lisbon in 1755, and is always sitting there thinking this is just, another way God tests you, and this is still the best of all possible worlds. And of course, Voltaire is wickedly pointing a finger at the stupidity of that entire thought. And so this whole school, what's called optimism, pretty much vanished from Europe after the 1755 quake. Other examples you talked about the 1996 San Francisco earthquake. It changed the course of San Francisco history in lots of ways, one of which, of course, was that it changed the way the city was configured. A lot of what was damaged, for example, in the 1989 quake was the Marina District, which was on landfill from the quake debris of 1906. So they compounded their own problems. And they also, one of the curious stories there, which I mentioned in the book, is the idea that the city council and the city fathers of San Francisco, after the quake was over and the fire was over and they were trying to rebuild as fast as possible, they suppressed any accounts of the quake at all. And they called it the San Francisco Fire, because they wanted people outside of San Francisco to think it was just a normal city fire like you might have in the East Coast, and the quake was either not important or non-existence, because they wanted the city to rise from the ashes as quickly as possible, and they knew that talking about earthquakes scared people. So they literally suppressed the true information and covered up the fact it was really the earthquake that was responsible for the fire, and blamed it all on the fire, which was, of course, deliberate conspiracy. And the geologists who wrote the report complained actively about this, and it's in my book that they talk about it. Or another example, the volcanic eruption at Krakatoa in 1883. Probably the biggest volcanic eruption in recent human history, at least that was affecting a large population. And it was so huge, of course, it changed climate for a few months, and darkened the skies and caused them to be red. But more importantly, it hit at a time when the Dutch colonial interests in what was then the Dutch West Indies, is now Indonesia and Malaysia. Those countries were, colonial kind of powers, but they were very much sort of on the decay side. They were colonial interests were falling apart, and there was not much being invested in anymore by the Dutch government. And the disaster of Krakatoa then exposed the weakness of the Dutch colonial masters, and of course sort of pushed the rest of the natives to fight for their own country, which they eventually got after the Second World War, when the Japanese had been invaded and then driven out. So it's sort of weakened the Dutch colonial control, and then the final straw was the Second World War. The one that actually is thought to be even more effective is a huge eruption that also happened in Indonesia about 40,000 years ago, and this is thought to have actually caused a genetic bottleneck in human populations, such that there were just a few thousand humans surviving this huge eruption, and then from them all the humans that we've lived in since then, because this has shown up in the genetic codes when they've done this cross-population studies across populations all over the world, that they seem to have a genetic bottleneck. It dates back to the time of this big eruption, and it shows up not only in human genomes, it shows up in some of our parasites, which means that our genomes are tracking similar things, which is pretty strong support that something unusual happened back then. There's still controversy about this, but this eruption is thought to be a really big one. It's thought to be a crucial moment. If it were any bigger, it suggests maybe humans might not be around to talk about it.
Wow, that's fascinating. It makes me think, we haven't really talked a lot about volcanic eruptions as catastrophe, aside from these that you've just brought up. Yellowstone. Recently, I think it was this last week, there was some research that came out suggesting that the eruption, when it erupts, might actually be bigger than we've estimated, because the plume beneath the volcano might actually be bigger than what we previously thought it to be. What kind of an effect, based on, like, comparatively, maybe compared to Krakatoa or the 40,000 year ago possible eruption, what kind of an effect on humanity would you think that Yellowstone might have?
Well, Yellowstone is a well-known example because we have good records from lots of places about how far its ash plume went. And if you work in ice age deposits anywhere in the Midwest, you can see several different volcanic ash layers out there in the ice age deposits that came all the way from Yellowstone and are found as far east as Kansas and Nebraska and Missouri. So if you put all that evidence together, and there's a map in my book that shows it, they can plot those various places where this ash fell, and it basically has a plume that covers the entire western U.S. pretty much to the Mississippi. So the whole region would have been blanketed in at least an inch or two of ash far away from the volcanic eruption, and of course many feet of ash close to the source. And that, it would be truly catastrophic. I mean, because not only would all the population there be struggling to survive under those conditions, but it would bring everything to a big standstill for a long time. And Yellowstone has done this several times in the last few million years, so it's always being watched very nervously. So has the caldera that underlies Mammoth Mountain, the big ski resort in the Owens Valley, California, near Bishop, California. That one last exploded about 800,000 years ago, And when it did, the so-called Bishop Tuff, which you can see outcrops all over the Bishop area of this giant ash flow that came out of that vent, it had left tuff deposits that cover virtually the whole western U.S., all the way to the Mississippi. And you can see it in isolated places where that's exposed. So, if any of those, your listeners and viewers were around for Mount St. Helens 1980, that was small potatoes by comparison.
Yeah, these super volcanoes are they're going to be they have been a match for evolution in the past, and they're going to be a match for evolution in the future.
Yep. The more we learn about them, the more frightening they become. Number one, because just like earthquakes, they're relatively unpredictable. I mean, they're getting to the point now where if you have a volcano that's starting to build up, then you can get enough warning and get people out of the immediate vicinity. And that was done successfully, for example, in 1991 with Mount Pinatubo in the Philippines. But on the other hand, Mount St. Helens 1980, we were all waiting for it to happen, and they thought they were far enough away, but a good number of people living on the north side of the mountain never made it because it erupted in an unexpected way. It erupted sideways rather than straight up, and that turned out to be something never seen before. So these things are full of surprises. Even as much as we know about them, there's also the issue that they can always be different than we expect or bigger than we expect, in which case you think you've taken every precaution you can, but it's not enough.
What led you to write this book, Catastrophes, in the first place? I mean, I'm sure as a geologist, you're looking back through geological time and seeing all sorts of evidence of volcanic eruptions, of movement of the crust, or floods, maybe not tornadoes, but what spurred your interest?
Well, I teach this almost twice a year, every year. So I'm used to the subject. I have it, down pat because I teach it to my introductory class in little pieces, right? One day it'll be volcanoes. A few weeks later it'll be earthquakes and tsunamis. They're all done in separate parts of the course. But I'm very familiar with the subject, having taught it lots of times and, prepared the lectures and found all the examples and all the rest. So it was something I sort of knew off the top of my head. It didn't take a lot of research to get the bulk of that book written. And then it was right after the 2004 Boxing Day tsunami in Indonesia, which killed so many people. We were watching all the coverage, my wife and I, on various news stations. And she said, there's a subject you should write a book about. Where she's always trying to think of another topic I can write about that will sell copies. So she said, to write a book about natural disasters. And I say, yeah, that's something I could definitely do. But I've had such a busy schedule. I've had other books ahead of it, and grant proposals and research and a lot of scientific projects. And of course, I teach a full load too. So it's not like you can just sit down and do it the day after it's suggested most of the time for me. And in this case, it got delayed for 2 years, and then longer. It was not 2009, and I chose not to go in the field with my family and stayed home instead and worked for 3 or 4 weeks. It's in the summertime with no kids running around, and that's when you get writing done. So I got it done in 2009, thinking that it would be out the next year. And then the publisher had various delays, and now they monkey with this or that. And the publishers are slow. You don't have any control over it once you send it to them. So we were supposed to have it out in 2010, and then it didn't make that deadline. And so as I was spring 2011, and 2 weeks before it was supposed to appear, people in marketing are saying, okay, if we have a natural disaster, we'll try to jump on the bandwagon and do some publicity to help people know this book exists. Not like we were trying to make the natural disaster happen or anything, but natural disasters happen just about every few months somewhere in the world. And lo and behold, we got a big one. So the day after Sendai, I had editorials in the Los Angeles Times, and I was on MSNBC and the BBC, and a week there, just crazy media frenzy where everyone wanted me, and I was happy to do what I could do. So,
what are your perceptions of how the media covered the Sendai quake and the fallout from the tsunami?
Compared to the past, I think it's a lot better. I mean, for one thing, you had lots of real footage. I mean, Japan is probably the most photographed country in the world because everybody has a video camera or a cell camera. Yeah. And so it's one that had a tremendous amount of video popularity. And that gave us, a much more accurate picture than what you would get if you just have these, talking heads and still images or even very little than that. And that's something to think about, by the way, because people get this perception because they are remembering recent events much more than past events, and they see these giant events like Japan and last year in Chile and Haiti and other places like that, and think, oh, there's more earthquakes now than there ever been, and they're the worst they've ever been. Well, geologically speaking, that's not true. It turns out if you look at the longer-term record of seismic activity, and it goes and it comes in like irregular patterns. There's no strong increase or decrease that seems to be trending in any particular way that we can tell. If you look back to the 1960s, which most people around are not old enough to remember anymore, I do, of course, I'm old enough, but the two biggest earthquakes in human history since seismographs were invented were both in the 1960s. The 1960 Chile quake, the biggest ever recorded, and then the second biggest ever recorded, the 1964 Good Friday earthquake in Alaska, the biggest in U.S. history. And those are still number one and number two. And the events that we've just had this last year have added more events in that range, but they haven't matched them. And the 1960s in general were seismically more active than any time up till now. And so there isn't any clear pattern that we're actually going to a period of more earthquakes or less earthquakes. We don't have a record long enough to tell that. It's more likely that there are periods when the quake activity increases and then decreases, and we just don't have a record long enough to know if this is something that's a pattern that's regular or just randomly going back and forth.
Yeah, and being human in the media, we like to put patterns where there might not be patterns. So there's always something that we like to see, find those patterns where they don't exist.
And that was very evident in the media coverage of this event. There was good coverage when it came to documenting what happened, where, and when. And that, of course, you can't miss when you have video footage with time markers scrolling on the bottom. But then you got all these people put on the air, and I saw quite a few of them who simply were not qualified to talk about any of this, and they would make these arm-waving explanations about, we're going into a period of many more earthquakes and serious consequences will follow. And there was one interview on Fox News where they had this guy who's an obvious quack, who has no credentials to talk about earthquakes at all, who got 5 minutes to just spout his garbage on national TV, and there was no challenge, no question, no background check to find out the guy has no reputation whatsoever in the scientific community. And before he got on, the reporter who was doing the segment did this thing where he put up a map of the Ring of Fire around the Pacific, and he points to the Chile quake, and then the Sendai quake, and he starts with Haiti, then Chile, then Sendai, and then around the ring, and says, what are we in California do next? Well, any geologist, even an introductory geologist student who could tell you there's no connection there. They're all different kinds of plate boundaries. There's no evidence that any of them are actually connected. And so I actually wrote a blog post on this a few weeks ago and said they've done the research. In fact, there was a new paper out just after the earthquake confirming it, that these quakes are all completely independent. There's no reason to think they're connected. They're not even on the same plate boundaries. They're not the same motions. And if you look at the longer-term record, that's the case. It's just we humans like to, as you said, like to make patterns, like to think things are connected, and there's no statistical basis to establish that whatsoever, which is what a scientist requires.
Yeah, and we would hope that the reporter or other reporters would pick up on the follow-up that scientists like you are putting out there into the blogosphere, into the world, so that the public can actually find out what's going on, as opposed to just hearing reporter speculation. I'm curious about your research and what else you actually do other than focus on catastrophes. I mean, catastrophes can probably get to be a little bit depressing after a while. So I'm sure there's got to be other work in your life. What's going on?
Well, actually, this book is really sort of far away from what I do in my research. It's connected with my teaching a lot, and so I'm pretty familiar with all the background I have since graduate school, and so it didn't take much work for me to put this book together. But my primary training is as a paleontologist. I'm one of those kids who got hooked on dinosaurs at age 4 and never grew up. Except that I got hooked on age 4 dinosaurs in the 1950s when they were not cool, and most kids were not interested in them. I was the only one in my high school or class or even younger who were interested in dinosaurs. I was considered sort of an oddball for that reason. Now every kid, of course, goes through a dinosaur phase that lasts right about till puberty. And so it's something that's, it's been fun in some ways because I've done essentially what I intended. As soon as I knew what a paleontologist was, I knew what I wanted to do, and I've been successful getting there. So most of my research and many of my books are really about the kind of paleontology I do. I work on fossil mammals like rhinos and horses and camels over the last 45, 50 million years primarily. And so I study lots and lots of different kinds of fossils. My research began in the Big Badlands, South Dakota, with a new technique called magnetic stratigraphy, which allows you to date beds, to the nearest few thousand years when there was no dating like that before. And I've done that kind of work virtually everywhere in the western U.S. now, from British Columbia down to Baja. And it gives me a chance every summer to go someplace different and do a new project. And the grant money comes to pay actually for that kind of geophysical work. I've never gotten a single grant dollar in my whole life to actually do paleontology because there isn't any. But it's been fun. It's what I enjoy doing. Lately, I've had students working with me a lot here at Occidental. We have undergrads only, so they get to do research before they graduate here. In fact, they're expected to. And so my last group of students starting in 2008, and I've just pretty much got them all into this project. We've been looking at Rancho La Brea, the La Brea tar pits, which are about a half an hour from here. And there's a tremendous record of the last 40,000 years of evolution and climate there. And what we've been doing, each student takes a different animal, a different bird or a different mammal from Rancho La Brea. And it's a great project for students because I loan them a pair of calipers. They all have a laptop. They all know how to run Excel. And so we jump in and they measure the heck out of those specimens, as many bones from as many well-dated pits as we can find. And we've been looking at the patterns of evolutionary change over time in these animals. And what's striking about this is something that was predicted now almost 40 years ago by Stephen Jay Gould and Niles Eldridge, who were pioneers of my profession. I was actually a student of Niles and a protege of Stephen Jay Gould, was that you would expect no change at all when the climate changes. And this time interval we're talking about, the last 40,000 years, includes the last full glacial cycle and then the present interglacial interval we're in right now. And so we can see exactly what the mammals did when the climate changed, and the birds as well. And the answer is they didn't give a damn, to paraphrase Rhett Butler. They do show no change in size or shape despite one of the biggest climate changes of the last 40,000 years. They march straight through. So it's a really interesting conclusion because this is something people like Gould and Eldridge and their followers would have predicted, but it goes against models of evolution that are based on the idea that organisms are infinitely flexible, and like Galapagos finches, they just respond in a few years to a climate shift. Well, the paleontologists have said something very different now for 40 years, that it appears that organisms tend to be very stable no matter what the climate does, and it takes unusual events to cause them to either speciate or go extinct, but they don't tend to gradually track the environment like our short-term perspective as neontologists might tell us. And so we're working this project out bit by bit. Each student has done a different animal. I just had one about to graduate in a few weeks who finished the dire wolves, which is the biggest group of all, the most common animal at La Brea. And I've got 5 or 6 of the most common birds there measured as well. So once this last few things have gone through the mill and each student gets their name on their own work, I'll probably put together a big, massive work with 20 co-authors and publish it somewhere where it'll get a little more attention. So that's been my latest project. But then I'm on sabbatical in 2.5 weeks. And as soon as my sabbatical starts, I'm going to be invisible on this campus. I'll stay home and work and write because I've got 2 textbooks I've got to update. I expect to spend some time in New York City, work in the American Museum of Natural History, where I was trained. I'm working now on fossil peccaries, or javelinas, the pig-like things you see in the desert Southwest and Central and South America, which are a very important group that was exclusively American their whole history, primarily North American most of their history, and yet there hasn't been a recent revision of them in over a century. And there's tons and tons of undescribed fossils in the American Museum collection in New York where I was trained. So someone like me who knows the collection well and knows what he's doing can go in a few weeks and pretty much put it all together. So I've done parts of it already, or parts of it already been published. I'm hoping to get enough of it finished this sabbatical that I can put it together into a book-length project. The last one I did was on North American rhinos, which was published in 2005, and that was only 25 years of my life in that book. So, but in many ways,
let's get more years in one book. Exactly.
Yeah, I know. Well, and there's North American camels are still waiting to be worked on. I don't know. I'll have to wait till I retire for that one. But there's so much to be done. I mean, we have these gigantic collections, 7 floors of fossil mammals, most of which have never been studied in just the American Museum in New York. And those of us who have the training to do this kind of work and can do it efficiently because we don't have to look up every locality as we go, it's just an amazing project. And for me especially, because as a paleontologist, I'm confident that most of my scientific work will hold up for the test of time. But fads come and fads go, and certain ideas become more important than others. But in paleontology, the stuff that lasts the longest is basic systematics of fossils. Just what are they? How do you recognize them? What is the proper name for them? It may not sound glamorous, but that is the foundation on which everything else we do is based. You can't do fancy computer curves of diversity through time if you don't have the number of animals right and their names right. And yet people do that on data sets that are not yet mature enough to do. And so a work like mine, I ended up in the rhinos, for example, syncing about 100 taxa that were invalid and creating a few new ones that really were new things, but syncing more than I created. And I've already done that with some other groups as well. And yet there have been publications out there that are based on all these names that we knew were invalid for many, many years, and simply no one had taken the time to do that kind of work. And to me, especially as a paleontologist, it's common that I work with monographs that are over 100 years old all the time, because the work that somebody did in 1880 or 1890 establishes the concepts of species they used, what specimens were the species based on. You have to go all the way to the beginning to works that are often 100 years old or more to do this kind of study. And you sit there in a collection, you're holding a specimen that was first described by Edward Drinker Cope in 1882. So you're actually touching something that Cope touched, or touching something that O.C. Marsh at Yale touched. And you know that there's a direct connection between you and that giant of the profession 100 years ago. And the work that we do in systematics tends not to be overthrown as often. It tends mostly to become more or less the most persistent and the most useful work we do, because I'm expecting for decades to come, it's something as big as my rhino monograph from 2005, it's unlikely anyone will ever have that big a fresh sample to do again, and will have any reason to redo that work on a large scale. So it probably outlived me by many generations, which is kind of immortality not many scientists can talk about.
But it's really exciting. There's a certain amount of, I guess, in many more, I guess, dynamic areas of science, the people tend to go for the glamour, the glitz and the glamour, and what can get more attention, from the media, or even get you more attention within the scientific community. But that work might, be eclipsed by other work within, a year or two, just based on a couple of experiments. Whereas the work that you're doing, like you said, can live on for generations, which is, I think, a much bigger bigger way to influence science in general. I'm also thinking, you're talking about the climate change aspects of looking at climate and the persistence of species over several years. I think it's a fascinating way you can look at something, a persistent sample of species, and be able to look at the climates, look at the geological record of what was happening during different time periods, what species existed, how they changed over time, and maybe get some kind of an idea of how things are going to change with our currently changing climate.
Yeah, that has been an angle that a number of paleontologists have been working on in recent years, particularly people like Tony Bernowski at Berkeley and his students. They worked largely on Ice Age mammals, or mammals from fairly recent periods where we know a lot about climate. And that is, as it says with the Rancho La Brea example, that's a place where you can do a lot of stuff, because most animals from the Ice Age, especially small mammals, are still alive today. And in many cases, the Ice Age material is young enough that it still has original organic material in it. You can still extract DNA from it. In many cases, you can do a lot of stuff you simply couldn't do with older fossils. You have huge sample sizes. You have great time control. So it allows us to really see a very precise window of what's going on in just about any organism you want at any time you want, depending upon what you're looking for. And so the main pitch they've been making, which has been very successful, is that they're trying to get a sense of what organisms do when climate changes, and then be able to do this as a way of predicting what to expect if we change the planet, as we're already starting to do right now, and what will survive and what won't, and what will it take to keep organisms alive versus drive them over the cliff. And so that's been something that's very successful, and they've been funded quite well as a result. All paleontologists have to think of an angle, to get the public to interested in what they're doing, or at least some percentage of the scientific community, NSF, interested in what they're doing, so that you can sell it as something the public would care about and has an application outside of your personal interests. And so, we always try to find ways to connect what we're doing to everything we're doing. It's not always just impractical stuff that we're just interested in because it's interesting. And there is that element in it, but a lot of people are looking forward and looking broadly interdisciplinary rather than just focused on one small group of animals.
Do you include the current climate change as a catastrophe in your categorization
Yes, as a
of
matter of fact,
catastrophes?
in the last chapters of my book, you'll see there's a whole chapter on both glaciation and what causes it, and then a chapter on greenhouse climates and when they've occurred and what causes it and what's going on with the present thing. And I actually talk at great length about the political and social side of this debate we've been having over what is this closed issue in the science community, but it's all a political issue now. So that's something that I take on as directly as I can. As a scientist, I have to report what my community says and call it where as I see it, let the chips fall where they may. So in many ways, it's for people who are sitting on the fence about global warming, this is a strongly worded book, but nobody in my profession finds this at all objectionable. We all know what we've been seeing for years. It's only the outside world that doesn't know how science works that's still debating it.
And that brings us to the end of our show. Thank you so much for joining me today, Dr. Prothero. This has been a really interesting conversation. I mean, everybody is waiting for the big one, whether it's a big earthquake, a big volcanic eruption. There's some catastrophe somewhere. Is it a tornado in the Plain States? Is it an earthquake here in San Francisco? There's always something that you should be prepared for, and it's neat to have a kind of a scientific history of what's happened and what's affected humans previously. I suggest everyone out there, if you have the time and the opportunity, go visit Amazon.com and get yourself a copy of Catastrophes by Dr. Donald Prothero. You can also find Dr. Prothero on Facebook. He has a Facebook account as well. So thank you very much. I do appreciate your time today.
Thank you very much, Kiki. I had a great time.
Yeah, it's been really great. You are a font of catastrophic knowledge.
Thank you.
You're welcome. And I'm Dr. Kiki. This has been Dr. Kiki's Science Hour. Be sure to tune in next week, and I am going to be interviewing Andrew Revkin of the New York Times .Earth blog. So I hope you tune in for that one. I think it's going to be a very interesting conversation. You can find me online. I'm Dr. Kiki on Twitter and also on Facebook. Just look me up in the Googles. In the Googles, you can find me. You can also subscribe to Dr. Kiki's Science Hour in iTunes, or you can find past episodes at twit.tv/Kiki, Kiki. Thanks for tuning into the Science Hour. All I ask is 1 hour of week. And I hope that this 1 hour makes your world a whole lot more interesting. Bye.